Good evening, ladies and gentlemen. How are you all doing? That is good to hear, and better because there are no more clouds. So I assume you're busy with your moon assignment. Ah, so while we are on that topic, so in the last 2 weeks, a few of you have come to see me during consultation sessions. So remember, I will continue consultation sessions until the semester ends. I will try to be on campus on Mondays and Tuesdays. But otherwise, we can schedule consultation sessions other times as well. And by these consultation sessions, it was good meeting a few of you in person. So if you're more than welcome to pop in for consultation if you have any questions. And then secondly, please do not underestimate the moon assignment. So have you guys at least attempted the moon assignment yet or start looking at it? So, Mr. Melville, I assume that is a shocked face. Cool. Why is the class so quiet this evening? Is everyone all right? Understand. So now this year has kicked off with a bang already. It's almost recess, if I'm not mistaken. So why are you all down bad? I understand. So luckily there's a long weekend not too far away. How are your semester tests going? Okay, so a bit of a mixed feeling. So why rough? I understand. So I see we are 38 people in tonight's class. Is something happening else this week? Perhaps a few semester tests or assignments happening this week? Okay. I understand. So let's start with tonight's lecture. So last night we ended off with supernova explosions of massive stars. But the next section is how to classify supernova. So do you guys have any idea how we will classify supernova? So as you can see, we and they make some of the most beautiful objects we can observe. So if we go back to this previous image, we can classify it by looking at its spectra. So we've learned a lot about spectra already. So here we can see the reddish color is silicon, sulfur, calcium, iron, and this is the blast wave of the supernova. So if we put it all together, then we get this pretty image. So according to this, supernova can be classified. So a supernova occurs when a star with degenerate core collapses, but astronomers have found different kinds of supernova. Those that do not have hydrogen lines in the spectra are called type 1 supernovae, and those that do have hydrogen lines are type 2 supernovae. So these are a hint for the test and exams that I can ask you to, what is the two classifications, or give me a definition of the classification of supernovae. So massive star with a degenerate core can collapse and produce a supernova. These are classified type 2 and contain hydrogen lines in a spectra because though massive stars contains lots of hydrogen, but there are other ways a star with degenerate interior can collapse. So supernova can occur if a white dwarf in a binary system gains mass from its companion, exceeds the Chandrasekhar limit, and collapses. The interior of the white dwarf is degenerate, and the collapse begins. Temperature and density increase, and a hydrogen-oxygen core begins to fuse. Because gas is degenerate, there is no thermostat to regulate the fusion, and the entire white dwarf fuses suddenly in a violent explosion classified as a 1A supernova. The much less common type 1b supernova can occur if a massive star loses its hydrogen-rich outer layers to a companion star. The remains of the massive star can develop a degenerate core and collapse, as described in a previous section, producing a supernova explosion that lacks hydrogen lines. And a type 1b supernova is just a type 2 supernova in which the star has lost its outer layers. Because supernovae are so rare, they are difficult to observe. Astronomers must depend on historical records. Some records go back centuries, but more recent supernovae give astronomers the best evidence against which to test their theories. In the year 1054, Chinese astronomers saw a guest star appear in a constellation we know as Taurus. It became so bright it was visible in daytime for a month and took nearly 2 years to fade from sight. At the site of that ancient supernova, modern telescopes reveal a many-legged nebula known as the Crab Nebula. Doppler shifts showed that the nebula is expanding at 1,400 kilometers per second, and it is now about 1.4 parsec in radius. Dividing distance by velocity reveals that a nebula began expanding 9 or 10 centuries ago, about when a guest star was seen. The hazy glow inside the expanding filaments of the Crab Nebula is synchrotron radiation that is produced by high-speed electrons spiraling through a magnetic field. So this bright glow, the glow produced by synchrotron radiation, these filaments of gas rush away from the site of the supernova. So the Crab Nebula is located in the constellation we know as Taurus the Bull, just where Chinese astronomers saw a brilliant guest star in the year 1054. Over tens of years, astronomers can measure the motions of the filaments as they expand away from the center. Doppler shifts confirm that the near side of the nebula is moving toward Earth. High-speed electrons produced by the central neutron stars spiral through the magnetic fields and produce the foggy glow that fills the nebula. So are you guys happy with the definition of synchrotron radiation? Awesome. So most supernovae are seen in distant galaxies. So here we can see robotic telescopes search every night for supernova flaring in other galaxies. When one is seen, astronomers can obtain spectra as well as record supernova's rise and decline in brightness to study the physics of the exploding star. If a supernova is seen in a nearby galaxy, it is sometimes possible to identify the star in earlier photos. So here we can see an ultraviolet photo of SN2005CS. Here we can see the visual image of it, and here we can see the infrared image of it. Type 1 supernovae are about 6 times more luminous at maximum than type 2, and they fade more slowly at first. So type 1 supernovae decline rapidly at first and then more slowly, but type 2 supernovae pause for about 100 days before beginning a steep decline. Supernovae 1987A was odd in that it did not rise directly to maximum brightness. These light curves have been adjusted to the maximum brightness. So here we can see a type 1, a type 2, and then there's weird supernova as well. So the star that exploded as a supernova 1987A had about 20 times the mass of the Sun. Interactions of the burst of light and gas expanding from the explosion of material lost by the star during previous stages as a blue giant and a red supergiant have produced rings around the central glow, as shown in the high-resolution image and artist's conception. A shock wave from the explosion is now expanding into a 1-year light diameter ring of gas, ejected roughly 20,000 years before the explosion. As that ring is excited, it is lighting up the region around it, revealing how the star shed mass before it collapsed. Supernovae typically leave behind shells of hot gas expanding outward at velocities as high as 20,000 kilometers per second, in carrying away a fifth of the mass of the star. The shells can sweep up more gas from the interstellar medium and heat it to produce a supernova remnant. The nebula remains of a supernova explosion. So here we can see a supernova remnant is an expanding bubble of hot gas created by a supernova explosion. As the remnant expands and pushes into neighboring gas, it can emit radiation at many wavelengths. Jets can be seen extending toward the left and right of gas A. So here you can see the supernova remnant in visual wavelengths, X-rays, and again in X-rays. Supernova remnants look quite delicate and do not survive very long. A few tens of thousands of years before they gradually mix with the interstellar medium and vanish. The Crab Nebula is a young remnant, only about 960 years old and about 9 light years in diameter. Older remnants can be larger. Some supernova remnants are visible only at radio and X-ray wavelengths. They have become too tenuous to emit detectable light, but a collision of the expanding hot gas with the interstellar medium can generate radio and X-ray radiation. You saw in a previous chapter that a compression of the interstellar medium by expanding supernova remnants can also trigger star formation. So here we can see, if we look at our Milky Way galaxy, so this is the center of our galaxy, and here we can see right over there the remnant of the Crab Nebula. And one of my colleagues at Hartranft did his PhD on the Crab Nebula, which makes him one of the experts in the world on the Crab Nebula. So, ladies and gentlemen, do you have any questions on the work we have done so far? Yes, I'm doing my PhD. So I'm doing my PhD in correlation. So correlation is now a new hot topic, especially in astronomy, because we are now moving over to correlating different data. So if you have a few telescopes looking at the same object at the same time, how do you compare those data from the different telescopes? So if you have telescope A, telescope B, telescope C, and all is looking at the exact same object at the exact same time, and you now have to compare each other's data to create a nice image, how do you do it? And that is where my research comes in. So when do you think so? I'm only starting my PhD this year. So last year I finished up my master's. So I'm only now starting with my PhD. So it will take about 2 to 3 years to finish. So some very advanced stats. So yes, some very advanced stats and mathematics, but more precisely the Fourier transform. So usually in astronomy, the Fourier transform is your best friend. Fourier, so let me just type it in the chat. Fourier transform. I know there's a lot of people pronounces Fourier at different ways. Europeans pronounce it as Fourier, so the proper British English is Fourier, but the Americans, for some weird reason, pronounce it as Fourier. But basically what a Fourier transform does is, if you look at data, so data coming from a telescope in the time domain, it basically looks like sine and cosine waves. But to understand what's going on, you need to transfer it into the frequency domain, and that is what a Fourier transform is used. So somewhere in calculus and in your physics courses, you will be doing the Fourier transform quite a lot. So for this lecture tonight, we are going to talk about neutron stars and black holes that we have touched on last night briefly. So for this stars, we're going to look at this lecture, we're going to look at neutron stars, black holes, and then compact objects with disks and jets. So I showed you this diagram last night. So here we can see we started with a stellar nebula. Then we went to average star, red giant, planetary nebula, and it died as a white dwarf. But now when we start looking at massive stars, they are born from the stellar nebula, becomes a super red giant, then becomes a supernova. Then from a supernova, it either becomes a neutron star or a black hole. And that is what we are going to discuss tonight. So what circumstances lets the supernova create a neutron star? And what instances lets the supernova create a black hole? So in the last two chapters, you have traced the story of stars from birth to death. By now, you may be asking a simple question: what's left? The answer depends on the mass of the star. You already know that stars, like the Sun, produce white dwarf corpses, but more massive stars leave behind the strangest beasts in the cosmic zoo. Now, you are ready to meet neutron stars and black holes, and your exploration will answer four essential questions. How does Fury predict the existence of neutron stars? How do astronomers know neutron stars really exist? How does Fury predict the existence of black holes? And how can astronomers know that black holes really exist? So, what can you guys tell me about black holes and neutron stars? Let's have a little bit of a discussion first. Besides that a black hole are black, what can you tell me? Yes, so neutron stars are very dense, but a black hole's singularity is also very dense. Isn't a black hole caused by an exploding star? So yes, that is the supernova. So when a massive star explodes, that's a supernova, and that causes a black hole. Black holes bend light. Yes, that is correct. So the physics is pretty rough. Yes, physics are for these objects are pretty rough. But luckily, this is just an overview of the subject. So next year, when you're taking physics 210, I think, then you will do the physics more in depthly. Then concealing, because they absorb all visible light. Not all visible light, they literally absorb all of the electromagnetic spectrum. One sucks in matter, immense amount of energy. That is true. Immense amounts of gravity. That is also true. So, Mr. Melville, you say neutron stars may contain a substance that is so stable it will make everything else stable type of substance that kills all of an atom of its hits the Earth. That is also very true. So we don't know what happens inside a black hole. That is true. So is it true that a gravitational pull on a horizon is stronger when the black hole is smaller? So it all depends on the size of the black hole, but a black hole size depends on what mass originally the host star had. So usually we will discuss now if it is there's an event horizon around a black hole, and that is the point of no return. So if you are outside of the event horizon, then you still have a chance to escape the pull of the black hole's gravitational pull. But if you're inside the event horizon, then you can't escape the gravitational pull of the black hole. And not even light can escape it. So then you're in a bit of trouble. So gravity always wins. No matter how long a star struggles to withstand its own gravity, it must eventually exhaust its fuels and die by collapsing. Those stars that do not destroy themselves in the process become one of three types of compact disks: white dwarfs, neutron stars, or black holes. So we have discussed white dwarfs already, but now we are left with neutron stars and black holes. So, sir, what's your opinion on interstellar view and a black hole? So the movie Interstellar, that is actually quite interesting. So it is a sci-fi movie, so they need to explain a black hole in some way. But all the physics in the movie makes sense until they actually enter the black hole. Then that is where the movie becomes a little bit wonky. So we have no idea what's happening in a black hole, but I disagree of what is happening in the stellar in a black hole. So everything in the movie is spot on perfect until they reach the black hole. So something interesting for you, for your sci-fi fans, thinking about Star Wars and Star Trek. Let's take Star Wars, for example. When you have those nice big space battles and you have your X-Wings and TIE fighters fighting each other, and you can actually see they are banking quite fast and you hear the sound of their blasters. That's false. In space, you won't hear any blaster shots. Do you guys know why? Yes, you're right, it's a vacuum. Sound needs a medium to propagate through. So in sci-fi movies, when you hear shooting in space, even explosions in space, you won't hear anything. You won't even hear engines in space. And then, secondly, in the sci-fi movies, you see those spaceships making all those fancy quick turns left, right, up, down, dodging torpedoes, dodging lasers. That's also false. You guys know why? Again, it's a vacuum. There's no air resistance. So if you have a fighter jet and you quickly want to bank left or turn left quickly, then you deploy flaps and you actually use the air resistance to turn you and do all those fancy maneuvers. But in space, you don't have any air resistance, so you won't be able to do those maneuvers. So how do you turn in space? So that is where orbital mechanics comes in. So orbital mechanics is a bit differently. So if you want to go higher, for example, above a planet, you need to go faster. If you want to go lower, you need to go slower. And then everything comes down to Newton's third law. So for every action, you have an opposite and equivalent power reaction. So you actually use your thrusters to move. And that is how you turn in space. So if you got sucked into a black hole, then due to its immense gravity, time relative to the rest of Earth would flow very slowly, so people would see you falling into a black hole for a very long time. Would it therefore be possible that in this time humans could advance enough to actually save you before you die? That is actually a very good question. It comes down to the time paradox that you will be discussing in other physics modules in depthly, but theoretically, no. So from out, it all depends on your reference frame. So for observer on the outside of the event horizon, it will seem like you will be falling for a very long time because they are actually seeing the last pieces of light before you enter the event horizon. But inside the event horizon, you are on a totally, completely different reference frame. So you would be falling, so you would reach the singularity actually. You will reach it, but you will die because due to the immense gravitational pull. But unfortunately, no, they won't be able to save you. So, but if there is no air resistance, what would the thrusters pushed against? That comes down to Newton's third law again. So let me get a whiteboard out. This will be easier to explain. I know this is a bit mind-boggling in space, but this is actually how it works. This is a nice example of Newton's third law. So let's draw our spaceship. So here is our rocket. So in space, what actually happens is, here we have our flames, or our propulsion, and our gases coming out. So what actually happens is, this comes down to Newton's third law. So let's say we can draw an imaginary line in here. So what this means is, we have a force pushing this way, but this means the fuselage of the rocket has to counter the force in exactly that way. And these forces pushing against one another and counteracting one another is what's making the rocket move in a certain direction. So I know it's a bit mind-boggling and a bit counterintuitive, but that is actually how you travel and navigate in space. So a neutron star containing a little over one solar mass compressed to a radius of about 10 kilometers can be produced by type 2 supernovae. For comparison, a white dwarf has about the same mass, but is about the size of Earth. A neutron star's density is so high that physicists calculate this material as stable only as a fluid of neutrons. Theory predict that such an object would spin a number of times a second, be nearly as hot as its surface as inside of the Sun, and have a magnetic field a trillion times stronger than Earth's. Two questions should occur to you immediately. Firstly, how could any theory predict such a bizarre object? And secondly, do neutron stars really exist? Neutrons were discovered in a laboratory in February in 1932. Only 2 years later, in January 1934, Caltech astronomers Walter Baade and Fritz Zwicky published a seminal paper. They showed that some novae in historical records were much more luminous than the rest and suggested that these were caused by the collapse of a massive star core, resulting in an explosion they named a supernova. The core of the star, they proposed, would form a small and tremendously dense sphere of neutrons, and Zwicky coined the term neutron star. Something quite interesting. The most difficult university to get into is Caltech. I don't know if you guys realize that. Big Bang vibes, and you guys know why it's so difficult to get into Caltech? Not because Sheldon Cooper is here, it's because they have a maximum of 8,000 students. So UP have roughly, from first year all the way up to PhD level, roughly 55,000 students. Caltech only has 8,000 students. That's it. From those 8,000 students, 3,000 is undergraduate and 5,000 is postgraduate. So they literally don't have space to take in more students, and because they're doing quite extensive research, so they literally take the best of the best of the best to be accepted to Caltech. And something interesting, Caltech also doesn't have a medical school. Caltech primarily focus on physics and engineering. Do they have an art school? I'm not sure if they have an art school. So over the following years, scientists applied the principles of quantum mechanics to see if such an object was indeed possible. Neutrons spin in much the way that electrons do, which means that neutrons must obey the Pauli exclusion principle. In other words, if neutrons are packed together tightly enough, they can become degenerate just as electrons do. White dwarfs are supported by degenerate electrons, and quantum mechanics predicts that an even denser mass of neutrons could support itself by the pressure of degenerate neutrons. So how does the core of a collapsing star become a mass of neutrinos? Nuclear physics provide an explanation. As the supernova begins, the core collapses inward. If the collapsing core is more massive than the Chandrasekhar limit of 1.4 solar masses, then it cannot reach stability as a white dwarf because the weight is too great to be supported by degenerate electrons. The collapse of the core continues, and atomic nuclei are broken apart by gamma rays. Almost instantly, the increasing density forces the freed protons to combine with electrons and become neutrons by this reaction. So you guys don't need to know this equation whatsoever. This is just to give you the background on this work. So as a result of the production of each neutron is a neutrino. You learned in a previous chapter that a burst of neutrinos during a supernova explosion helps blast the envelope of the star away. The star's core is left behind as a neutron star. So, if we look at these type stars, which stars will produce neutron stars as remnants? Any idea, guys? O yes, B yes, A yes. What's the definition? Will you classify a point or a line where things will start happening? At B. So let's see. So as you learned in the previous chapter, a star that begins its life with less than about 8 solar masses can lose enough mass to die by forming a planetary nebula and then leaving behind a white dwarf. More massive stars also lose mass rapidly, but model calculations indicate they cannot shed mass fast enough to reduce their mass below the Chandrasekhar limit. So it seems likely that they must die in supernova explosions. Theoretical calculations suggest that stars that begin life on a main sequence with roughly 8 to 20 solar masses will leave behind a neutron star. Stars even more massive than that are thought to form black holes. So that is where the distinction lies between it. So what is the Chandrasekhar limit? So do you guys want a recap of the Chandrasekhar limit? Okay, let me quickly find that slide again. Okay, let me go back to last night's lecture slides. So here it is. So this was by the physicist Chandrasekhar. So what it basically says is, so if you add mass to a white dwarf, then its radius will shrink because you add mass to it, and the increased mass will be creating increased gravity, and that will squeeze it very tighter. So if you had enough mass to raise its total mass to about 1.4 solar masses, so that means 1.4 times the mass of our sun, the equation predicts that its radius will shrink to zero. And this is called the Chandrasekhar limit. So what that means is the more massive a white dwarf is, the smaller its radius is. And objects more massive than the Chandrasekhar limit can't be white dwarfs. So the Chandrasekhar limit is 1.4 solar masses. So if you add to a white dwarf more mass that is more than 1.4 solar masses, then it can't become a white dwarf. Then it will become either a neutron star or a black hole. Does that make sense? Is that a better explanation? Awesome. So if you are struggling with a certain concept, please stop me anytime. So let's go back to the slide we left off. So we know now that a theoretical calculation suggests that if we have a star that has 8 to 20 solar masses, it will most likely become a neutron star. And if it's above 20 solar masses, then it will leave behind a black hole. So how massive can neutron stars be? That is a critical question and a difficult one to answer because scientists don't know the strength of pure neutron material. They can't make such material in a laboratory, so its properties must be predicted theoretically. The most widely accepted calculations suggest a neutron star cannot be more massive than about 3 solar masses. So if a neutron star were more massive than that, the degenerate neutrons would not be able to support a weight, and the object would collapse, presumably becoming a black hole. Two of the most massive neutron stars observed have masses of 1.9 solar mass and 2.74 solar masses. So evidence in favor of that hypothesis. So how big are neutron stars? So mathematical models predict that a neutron star should be only 10 or so kilometers in radius, which combined with a typical mass means it must have a density of 10 to the power 15 grams per cubic centimeter. This is roughly the density of an atomic nucleus. So you can think of a neutron star as matter with absolutely all the empty space squeezed out of it. On Earth, a sugar cube sized lump of this material would weigh more than 1 billion tons. So here can just to put it in perspective, a tennis ball and a road map illustrate the scale of a neutron star. Such an object containing slightly more mass than the Sun would fit with room to spare inside the beltway around Washington, D.C. Simple physics, the same physics you have used in previous chapters to understand normal stars, predicts that neutron stars should be hot, spin rapidly, and have strong magnetic fields. You have seen that contraction heats the gas in a star. As gas particles fall inward, they pick up speed, and when they collide, their high speeds become thermal energy. The sudden collapse of the core of a massive star to a radius of 10 kilometers should heat to 1,000,000,000,000 degrees. Astronomers calculate that neutron stars should initially cool rapidly from the astonishing high temperature because neutrinos can't escape from their entire volume and carry energy away. After a few years, neutrino stars will cool down to a mere million degrees or so, and neutrinos won't be produced in bulk. From that point on, neutrinos should cool slowly because the heat can escape only from the surface, and neutron stars are so small they have little surfaces from which to radiate. The principle of conservation of angular momentum predicts that neutron stars should spin rapidly. All stars rotate because they form from swirling clouds of interstellar matter. As the star collapses, it must rotate faster because it conserves angular momentum. If the Sun collapsed to a radius of 10 kilometers, its rate of rotation would increase from once every 24.5 days to more than 2,000 times per second. You might expect the collapse of a core of a massive star to rotate in a range of 10 to 1,000 times a second. It isn't hard to understand how a neutron star could have a powerful magnetic field. All stars have magnetic fields, and some have fields 1,000 times stronger than the Sun's. The field is frozen into the ionized gas of a star, and when it collapses into a neutron star, the field is squeezed down, concentrated, and made as much as 1 billion times stronger. So, speaking about magnetic fields, have you guys ever thought about the power and strength of magnetic fields? So, if you take a normal fridge magnet, what do you guys guess will be the magnetic strength of a normal fridge magnet? So Mr. Mark Saffron, then you are correct. So depending on the size and your magnet you're using, that can be 0.05 Tesla all the way up to a few million, even micro Tesla. But the most powerful magnetic fields we can generate on Earth are in CERN, the Large Hadron Collider. Do you guys have an estimate of what those magnetic field strengths are? So you can guess a little bit higher, you can guess more. So, what do you say? A trillion? So, trillion is a bad eye. So, it depends on what your experiment, but the main dipoles of the Large Hadron Collider can generate a magnetic field of 8.3 Tesla. So, just to put that into perspective, 8.3 Tesla is 100,000 times more powerful than Earth's magnetic field. So Earth's magnetic field is roughly between 25,000 and 65,000 nanotesla. So yes, a tokamak reactor can make 13 Tesla magnetic field, but that is because you need immense magnetic fields in those reactors to sustain the nuclear fusion process. I've actually forgot about those reactors. So how do they generate that magnetic field? That is being generated by uh, electromagnets. So we all know if you have let's say, a current moving through something. Um, so that means you have electrons flowing. And as soon as you have electrons flowing, you have an electric field. And if you have an electric field, you have a magnetic field. And usually the larger the electric field is, the larger the magnetic field is. So then you can construct an electromagnet that can create that immense uh, gravitational fields. So have you guys ever built an electromagnet before? That is something all of you should do at one point. You just need a wire that you twist around something. So easiest is usually if you just take a pencil and you twist wire around it and you take a battery, then you can create an electromagnet. So theory predicts the properties of neutron stars, but it also predicts that they should be difficult to observe. So does it better with an iron core. So yes, that can help. But yes, Mr. Tim, you are correct. So if you did in Science Project 7, grade 7, you just make a solenoid. So in next week's class, I will just show you, or tomorrow, I will just send on a group a link of how to make an electromagnet. So theory predicts the properties of neutron stars, but it also predicts that they should be difficult to observe. Neutron stars are very hot, so from your understanding of black body radiation, you can predict that they will radiate most of the energy in a gamma ray and X-ray part of the spectrum. Radiation that could not be observed in the 1940s and 1950s because astronomers could not yet put telescopes above Earth's atmosphere. Also, the small surface areas of neutron stars mean they will be faint objects. Consequently, astronomers of the mid-20th century were not surprised that none of their newly predicted neutron stars had been found. Neutron stars were at that point entirely theoretical objects. So, do you all know who this is? Yes, you're right, Mr. Marvel. This is Professor Dame Jocelyn Bell Burnell. So she was being nominated for a Nobel Prize a few times for her discovery of pulsars, that's for part of a neutron star. But unfortunately, she did not receive a Nobel Prize for her work, although she was nominated a few times, but she was knighted by the Queen. So she is Professor Dame Jocelyn Bell. She is a professor at Oxford University. So, in November 1967, Jocelyn Bell, a graduate student at Cambridge University in England, found a peculiar pattern in the data from a radio telescope. Unlike other radio signals from celestial bodies, this was a series of regular pulses. So, in this image, we can see 1967 detected of regular spaced pulses in the output of radio telescope led to discovery of pulsars. This record of radio signal from the first pulsar, CP1919, contains regularly spaced pulses marked by ticks. The period is roughly 1.33 seconds. So this was actually quite an interesting story because Cambridge controls a radio telescope. What is the telescope's name again? I will tell you now. Jodrell Bank telescope. It's a Jodrell Bank telescope that's controlled by Cambridge. And she was doing observations. And back in the 60s, it's not like today where we have our fancy computers and can store everything on hard drives. So back then, I don't remember if you watch old movies where they do a polygraph test on someone and you have that needle jumping up and down on a piece of paper. Do you guys have that image in your mind? So back then with radio telescopes, the same principle was used. So to get your data from a telescope, that was actually drawn on a piece of paper that was on a continuous roll that would just roll down, roll down, roll down, and it would draw it. So this would be the piece of paper, and this will be the with a marker. This will be the piece of paper, and then the needle will draw these marks. So here we can see a peak, a peak, a peak, a peak, a peak, a peak. So back then, the people from Jodrell Bank and Cambridge thought, well, there must be something wrong with the telescope. The telescope is not calibrated properly. So after a few days of observation, they realized, well, if they point this to a specific place in the sky, they get this pattern. So at first, she and the leader of the project, Anthony Hewish, thought the signal was interference from earthly sources, but I found it day after day in the same place in the sky. Clearly, it was celestial in origin. Another possibility that it came from a distant civilization led them to consider naming it LGM for Little Green Men. But within a few weeks, the team found three more objects in other parts of the sky pulsing with different periods. The objects were clearly natural, and the team dropped the name LGM in favor of pulsar, a contraction of pulsing star. The pulsing radio source Bell had observed with a radio telescope was the first known pulsar. As more pulsars were found, astronomers argued over their nature. The periods range from 0.033 to 3.75 seconds, and each one was nearly as exact as an atomic clock. However, months of observing showed that many of the periods were slowly growing longer by a few billionth of a second per day. Whatever produced the regular pulses had to be highly precise, nearly as exact as an atomic clock, but also gradually slowing down. It was easy to eliminate possibilities. Pulsars could not be ordinary stars. A normal star, even a small white dwarf, is much too big to pulse that fast. Nor could a star with a hard spot on its surface spin fast enough to produce the pulses. Even a small white dwarf would fly apart if it spun 30 times a second. So before continuing, are you guys familiar with atomic clocks? Okay, cool. So you guys are familiar with it. So why is it slowing down? We will discuss that momentarily. So yes, but a reminder of how they work would help. So atomic clock is basically you have a vacuum chamber, so a vacuum seal, and that vacuum chamber is more or less the size of a mini bar fridge. So inside, depending on what design you're using, so usually it's a methanol atomic clock or hydrogen atomic clock. So another word for it is a maser. So same principle as a laser. So light is light amplification by stimulation of emitted radiation. Maser is just microwave amplification by stimulation of emitted radiation. So let's take the methanol one, for example. So you pump in exactly one molecule of methanol inside that vacuum chamber, and you give it a slight electric current. So that means that methanol atom or particle will now oscillate up and down in the chamber. So once that's completed a movement from up to down, 1 second has exactly passed. And once it oscillates back and moves back from down to up in the vacuum chamber, another second has passed. And that is accurate to roughly 10 to the power minus 14th of a second. Some of the best atomic clocks we have is now at more or less 10 to the power minus 18th of a second. So something interesting is there are 8 atomic clocks in the on the African continent, and we have 3 of them at the Hartebeesthoek, so the Hartrau Observatory. Just something for interest's sake. So the pulses themselves gave the astronomers another clue. So why do you need 3 days? So what you guys don't actually know about the Hartrau or the Hartebeesthoek site is we actually play an important role. So everywhere where there's a telescope across the Earth is an atomic clock, so we need to timestamp it, especially when we observe the same object at the same time. But what makes Hartrau very important is we are the site in the world that is the best. I want to say, let's looking at the correct way to phrase this, we are the best measured and tapped into the GPS network. So if you do contour maps of certain areas, and if you're doing land surveying, you need to do it from a certain point. And that happens in Africa from Hartebeesthoek or Hartrau. So if the Hartrau site would go offline, that means the entire GPS network will also go offline. So that is why we make use of these atomic clocks. Something else interesting, if you say on your computer and on your phone, to update date and time, then you have to select your area in. So you usually have to select you are in Johannesburg or Pretoria or in Africa, and it's usually on a GMT or UTC +2 line. So that O2 update date and time for South Africa also comes from the Hartebeesthoek Hartrau site. So how has Eskom not messed up all of that? So we have backup generators for our backup generators. We have UPS systems. We have a UPS system for our UPS systems. Our atomic clocks is on their own separate foundation, so it's earthquake proof as well. And we are a national key point as well. So last year in June, when there was these riots, so in KZN and in Gauteng, we actually had army troops stationed at the observatory because we are a national key point and we cannot go offline. So the pulses themselves gave the astronomers another clue. The pulses last only about 0.001 seconds, placing an upper limit on the size of the object producing the pulse. If a white dwarf blinked and then off in that interval, you would not see a 0.01 second pulse. That's because the point on a white dwarf closest to Earth would be about 6,000 kilometers closer than its center, and light from that spot would arrive at 0.02 seconds before the light from the bulk of the white dwarf. As a result, its short blink would be smeared out into a longer pulse. This is an important principle in astronomy. An object cannot change its brightness appreciably in an interval shorter than the time light takes to cross its diameter. If pulses from pulsars are no longer than 0.01 second, then the objects cannot be larger than 300 kilometers in diameter and could be much smaller. So what would happen if it went offline? So if it went offline our site, that means in Africa you would have a bit of a trouble doing auto update date and time. So the time on your devices would differ. Your GPS accuracy will be off tremendously. And then also from our site also we monitor all, that's our geodesy program, we monitor all seismic equipment and seismometers across South Africa and Africa. So that will also be offline. And we won't be able to do observations because the telescope will then also be offline. And just to put in perspective, if one of our atomic clocks, so we also refer to them as maser clocks, goes offline, it will take us about 4 weeks to get one of them online again because you cannot just give it power and there you go. These clocks are highly temperature sensitive as well. So, for example, you cannot have more than 2 people at once in the room where these clocks are in, because half a degree in difference will make these clocks unstable. So these clocks are kept constantly at 24 degrees. So if these clocks needs to be serviced and maintenance needs to be done, only one person can enter, and it can only be there short periods of time, not to disturb and make these clocks unstable. So only a neutron star is small enough to be a pulsar. In fact, a neutron star is so small that it couldn't pulsate slowly enough, but it can spin as fast as 1,000 times a second without flying apart. The missing link between pulsars and neutron stars was found in 1968 when astronomers discovered a pulsar at the heart of the Crab Nebula. The Crab Nebula is a supernova remnant, and theory predicts that some supernova leave behind a neutron star. The short pulses can be discovered of the pulsar in the Crab Nebula with strong evidence that pulsars are neutron stars. So as you have noticed before, scientists often work by building a model of natural phenomena. Not a physical model made of plastic and glue, but the intellectual concept of how nature works in specific instances. The astronomer's model may be limited and incomplete, but it helps them organize their understanding. The modern model of a pulsar has been called a lighthouse model. So notice 3 important points. A pulsar does not pulse, but rather emits beams of radiation that sweep around the sky as a neutron star rotates. If the beam do not sweep over Earth, the pulses will not be detected by Earth's radio telescopes. Secondly, the mechanism that produces the beams involves extremely high energies and is not fully understood. Then thirdly, Modern space telescopes, observing from above Earth's atmosphere, can image details around young neutron stars and even locate isolated neutron stars whose beams of electromagnetic radiation do not sweep over Earth. When a pulsar first forms, it is spinning fast, perhaps 100 times a second. The energy it radiates into space comes from its energy of rotation. So as it blasts beams of radiation outward, its rotation slows. The average pulsar is apparently only a few million years old, and the oldest are about 10 million years old. Presumably older neutron stars rotate too slowly to generate detectable radio beams. You can expect that a young neutron star should emit powerful beams of radiation. The Crab Nebula as an example. Only about 960 years old, the Crab pulsar is so powerful it emits photons across the entire electromagnetic spectrum at radio, infrared, visible, X-ray, and gamma ray wavelengths. So before we continue with the evolution of pulsars, do you guys want to take a quick 5-minute break? Okay, so let's take a break and we will continue at 22.7, so 6:40. Yes, you may ask a question. You need deciding whether you should make something or eat or buy takeout. Any advice? That is a difficult question. So it all depends what you're in a mood for. So if you're in a mood for something specific, get something. Otherwise, make something. If you feel you will save more time by getting something, then go for it. So let's continue with this class. So now we're going to start looking at evolution of pulsars. So in this image, we can see High-speed images of the Crab Nebula pulsar show it pulsating at visual wavelengths and X-ray wavelengths. The period of pulsation is 33 milliseconds, and each cycle includes 2 pulses as its 2 beams of an equal intensity sweep over Earth. So here we can see the main pulse, and here we can see the secondary pulse. So then in an X-ray, we can see the main pulse and again the secondary pulse. So only the most energetic pulsars produce short wavelength photons and thus pulse at visible wavelengths. The Crab Nebula pulsar is young and powerful, and it produces visible light pulses. So does another young pulsar called the Vela pulsar, located in the Southern Hemisphere constellation Vela. So something quite interesting. A few telescopes in the Southern Hemisphere actually uses the Vela pulsar to calibrate their equipment on. So here we can see the pulsar, and here we can see a jet leaving the pulsar. So compared with most pulsars, the Vela pulsar is fast, pulsating about 11 times a second, and, like the Crab Nebula pulsar, it's located inside a supernova remnant. Its age is estimated at a roughly young 20 to 30,000 years. The Fermi Gamma Ray Space Telescope has detected a new kind of pulsar that pulses in pure gamma rays. It is not clear how these pulses are produced, but because gamma rays are extremely short wavelength, high energy photons, the process must involve very high energies. At least one of those gamma ray pulsars is located inside a supernova remnant that is only about 10,000 years old. So, let's take a look further at this. So the electromagnetic energy of the beams is just a small part of the energy emitted by a pulsar. Roughly 99.9% of the energy flowing away from a pulsar is carried as a pulsar wind of high-speed atomic particles. This can produce small, high-energy nebula near a young pulsar. So in this image, we can see the effects of a pulsar winds can be seen at X-ray wavelengths. The high energy gas of the winds is sometimes detectable, as is the interaction of the winds with surrounding gas. So not all pulsars have detectable winds. You might expect to find all pulsars inside supernova remnants, but the statistics must be examined with care. Many supernova remnants probably do contain pulsars, but their beams never sweep over Earth. Also, some pulsars move through space at high velocity, quickly leaving their supernova remnants behind. So here we can see many neutron stars have high velocities through space. Here is a neutron star known as RxJ18563533754. Was photographed on 3 different dates as it rushed past the background star. So here October 6, 1996, here March 30, 1999, and here September 16, 1999. Nearly 2,000 pulsars are now known, and some are located in binary systems. These pulsars are of special interest because astronomers can learn more about the neutron star by studying the orbital motion of the binary. Also, in some cases, mass can flow from a companion star onto the neutron star, and that produces high energy violence. The first binary pulsar was discovered in 1974 when astronomers Joseph Taylor and Russell Hulse noticed that the pulse period of the pulsar PSR B1913 plus 16 was changing. The period first grew longer and then grew shorter in a cycle that took over 7.7 hours. Thinking of the Doppler shift seen at spectroscopic binaries, the radio astronomers realized that a pulsar had to be in a binary system with an orbital period of 7.75 hours. When the orbital motion of the pulsar carries it away from Earth, astronomers see the pulse period lengthen slightly, so redshift. Then when the pulsar rounds its orbit and approaches Earth, they see the pulse's period shorten slightly, so just a blue shift. The resulting graph of radial velocity versus time was then analyzed to find the shape of the pulsar's orbit. So the analysis of the pulsar showed that a binary system consists of two neutron stars, one of which is silent, separated by a distance roughly equal to the radius of our Sun. So here we can see the binary. So here we can see the center of mass, and here we can see the hours, and where we can see the radial velocity out moving away from us and in towards us, away from us and then towards us. So yet another surprise was hidden in the motion of the pulsar. In 1916, Einstein's general theory of relativity described gravity as a curvature of spacetime. Einstein realized that any rapid change in gravitational fields should spread outward at a speed of light as gravitational radiation. Taylor and Hulse was able to show that the orbital period of the binary pulsar is slowly growing shorter because the stars are radiating orbital energy away at exactly the rate expected for gravitational radiation, and so are gradually spiraling towards each other. So normal binary stars are too far apart to orbit too slowly to emit significant gravitational radiation. So Taylor and Hulse won the Nobel Prize in 1993 for their work confirming general relativity using binary pulsars. In 2016, it was announced that a laser interferometer gravitational wave observatory, LIGO, that we talked about in an earlier chapter, had made a first direct detection of gravitational radiation. Dozens of pulsars have been found orbiting stars of various kinds. By analyzing the Doppler shifts in their pulse periods, astronomers can estimate the masses of the neutron stars. Typical masses are about 1.4 solar masses, as predicted by theory. In 2004, radio astronomers announced the discovery of a double pulsar, so two pulsars that orbit each other in only 2.4 hours. One spins 44 times a second and the other spins once every 2.8 seconds. The system is a pulsar jackpot because the orbits are nearly edge-on to Earth, and the powerful magnetic fields and the gas trapped in the fields eclipse each other, giving astronomers an opportunity to study their size and structure. Furthermore, the theory of general relativity predicts that these pulsars are emitting gravitational radiation so that their separation is decreasing by 7 millimeters per year. The two neutron stars will merge in 85 million years, presumably triggering a violent explosion. In the meantime, the steady decrease in orbital period can be measured, giving astronomers another test of general relativity and gravitational radiation. So question, so we could use gravitational radiation to send signals? In theory, yes, but in practice that would be very, very difficult. The gravitational fields of neutron stars are so strong they can be sites of titanic violence. An astronaut stepping onto the surface of a neutron star would instantly smushed into a layer of only 1 atom thick. So if you dropped an apple onto the surface of a neutron star from a large distance, it would hit with an impact equivalent to a megaton nuclear bomb. In general, a particle falling from a large distance to the surface of a neutron star will release energy equivalent to 0.2 mc squared, where m is the particle's mass at rest and c is the speed of light. So do you guys remember E equals mc squared? So Mr. Tim, so not lots of noise. So for us to create gravitational waves, we will need objects or something with extreme mass to create it. So here we can see an image A. Sometimes the X-ray pulses from Hercules X1 are on and sometimes they are off. A graph of X-ray intensity versus time looks like the light curve of an eclipsing binary. Then in image B, in Hercules X1, matter flows from a star onto an accretion disk around a neutron star, producing X-rays, which heat the near side of the star to 20,000 Kelvin, compared with only 7,000 Kelvin on the far side. So X-rays turn off from Earth's point of view, and when a neutron star is eclipsed behind the star. So in image A, we can see at visible wavelengths, the center of star cluster NGC 6624 is crowded with stars, but in image B, we can see in the ultraviolet one object stands out, an X-ray source consisting of a neutron star orbiting a white dwarf. Then image C, as an artist's conception, shows matter flowing from the white dwarf onto the accretion disk around the neutron star. Your knowledge of pulsars suggests that newborn pulsars should blink rapidly and old pulsars should blink slowly. In fact, the handful that blink the fastest may be quite old. The currently fastest known pulsar is catalogued as PSR J174824446AD. It pulses 716 times a second and is slowing down only slightly. A number of other very fast pulsars have been found. They are generally known as millisecond pulsars because their pulse periods, and therefore their periods of rotation, are around a millisecond. This rapid rotation produces some fascinating physics. If a neutron star, 10 kilometers in radius, spins 716 times per second, then its equator must be traveling at almost a sixth of the speed of light. So in this image, we can see the Black Widow pulsar and its companion star are moving rapidly through space, creating a shock wave like the bow wave of a speedboat. The shock wave confines high-energy particles shed by the pulsar into an elongated cocoon, and that is the red. So because a pulsar's period is so precise, astronomers can detect tiny variations by comparing their observations with atomic clocks. When astronomers checked pulsar PSR B1257 plus 12, they found variations in a period of pulsation, much like those caused by the orbital motion of binary pulsar. However, in the case of this pulsar, the variations were much smaller, and when they were interpreted as Doppler shifts, it became evident that a pulsar was being orbited by at least two objects with planet-like masses of 4.1 and 3.8 Earth masses. The gravitational tugs of these planets make the pulsar wobble about the center of mass of the system by more than 800 kilometers, producing the observed tiny changes in period. So this is what's happening. So you have the neutron star, and we have our two planets orbiting the neutron star. So in image A, we can see the data points in this graph represent observations showing that the period of the pulsar varies from its average value by just 10 trillionth of a second. The blue line indicates the variation that would be produced by a best fit model for these largest of the three planets orbiting the pulsar. Then in image B, as the planets orbit a pulsar, they cause it to wobble by less than 800 kilometers, a distance that is invisibly small in this diagram. So the outermost planet orbits about 0.46 AU from the pulsar. Further than Mercury, but closer than Venus, is from the Sun. So this is always something interesting. So there's a lot of work being done where in our data we try to create mathematical models to create the best fit as possible. So that's another field on its own. So now we are going to discuss black holes. So where is this image from, and what can you tell me about it? Yes, this is the first image of a black hole. You guys are correct. Yes, it was made by combining multiple images from multiple telescopes that form the Event Horizon Telescope. So right now, we have done everything up to a neutron star. So the only thing that remains now are black holes. What are black holes? How are they formed? And what do we know about them? So the first idea of a black hole was first proposed by English astronomer John Michell in 1784. So Mitchell's simplistic calculations assumed such a body might have the same density as the Sun, and concluded such a body would form when a star's diameter exceeds the Sun's by a factor of 500, and the surface escape velocity exceeds the speed of light. So in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. So this image to the left is Einstein when he was 25 years old. So in 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed new concepts of space and time. Einstein then spent 10 years trying to include acceleration in the theory and published his theory of general relativity in 1915. In it, he determined that massive objects cause a distortion in spacetime, which is felt as gravity. So here is, so you don't need to know this equation whatsoever. This is just something interesting to show how general relativity fits into a black hole. So in his work of general relativity, Einstein came up with the field equation for general relativity, but he did not solve the equation. He has to have the equation, but he did not solve the equation. So you don't need to know this whatsoever, but I thought this is an interesting derivation to show you of how to get to a few of Einstein's famous equations. So here we start by noting that energy is the internal integral of a force with respect to distance. So the kinetic energy K can be defined as follows. So kinetic energy K is force, and we integrate it in terms of distance. So where F is the force in the direction of displacement, ds, and S is the distance over which the force acts. So using Newton's second law of motion, we can write F as this integral form. So we can plug that into our equation. So this equation for kinetic energy can now be shown as follows, and that can be modified to get to this equation. So note that the velocity limit is c, the speed of light. So at c, time dilation becomes 100% and distances in the direction of motion shrink to 0. Hence a body at this speed will not experience time or distance, and so its velocity is set as the upper limit. So if we do integration by parts that I'm sure you guys are familiar with, and we added that integral, we can get to this equation right here, and that becomes a little bit more familiar. So the result shows that the kinetic energy of a body is equal to the increase in its mass as a consequence of its relative motion multiplied by c squared. This can be arranged in this following manner. So if the kinetic energy is decreased so that K equals 0, the body will be stationary, but it will still possess energy. In other words, the body contains energy when stationary relative to its frame and will have mass. This is called the rest mass, so this is shown as follows. So we can now solve this equation. This then completes the derivation of E equals mc squared for body at rest, and for moving body, its total energy is shown as follows. So here we have the body at rest, and here we have the moving body. Don't need to know this. This is something interesting I thought I should show you guys. So what is time dilation? So time dilation is what happens to time when you start moving at a speed of light. So we can actually measure time dilation. So in satellites, in GPS satellites, so it is the faster you are moving, the slower times becomes for yourself. So there is a interesting calculation. So say we can travel at a speed of light, and you are going to the closest star to us, Alpha Centauri. That's roughly 4.2 light years away. So if you're traveling at the speed of light and you are sitting on that spacecraft, it will take you 4.2 years to reach Alpha Centauri. And when traveling back, that will also take 4.2 years. So that means you have aged 8.4 years. But on Earth, time is perceived differently, and almost 100 years can go past on Earth in the time it took for you for you it's 8 years, but on Earth it's 100 years, and that is time dilation. I know that it screws up your mental thinking completely, but that's something you will do in your courses as well. So after Einstein published his theory, Karl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently achieved the same result of a point mass. So, speaking of this, do you guys know why we use point masses and spheres? It just makes the math easier. So here is the mathematical form of Einstein's gravity. So you don't need to know this equation at all, but it's just to give you background information. So here we have the scalar curvature, Newton's gravitational constant, stress energy tensor, the Ricci curvature tensor, metric tensor, cosmological constant, and light speed in a vacuum. And then we get to this bloke. So Stephen Hawking gave a more solid mathematical understanding to the concept of a black hole. So this is where we have now the Event Horizon Telescope. So that I was speaking about before, the Event Horizon Telescope is created by combining all these different telescopes together. And what makes these telescopes unique is that all these telescopes can observe X-rays. So in the 1970s, this was the best interpretation of how a black hole would look like. So just looking at Stephen Hawking's work, this was our guess of how a black hole looked like. Then we get to the Event Horizon Telescope, and this was the simulated image of how a black hole would look like. And then this was the actual first image of a black hole. You guys have any questions so far? Everybody still listening? Okay, cool. So now we're going to start speaking about escape velocity. So suppose you threw a baseball straight up. How fast must you throw it if it is not to come down? Of course, gravity will also pull back on a ball, slowing it. But if the ball is traveling fast enough to start with, it will never come to a stop and fall back. Such a ball will escape from Earth. So to escape from Earth, a spaceship would have to leave Earth's surface at 11.2 kilometers per second. But if you could launch spaceships from the top of a tower 1,000 miles high, the escape velocity would be only 10 kilometers per second. So to get this escape velocity, you are all sure, all know this equation. So we just solve for our speed v. You plug in our numbers and we have our escape velocity. So if you could make an object massive enough or small enough, its escape velocity could be greater than the speed of light. Albert Einstein's theory of special relativity, published in 1905, says that nothing can travel faster than the speed of light. So even photons, which have no mass, would be unable to escape. Such a compact, massive object could never be seen because light could not leave it. Long before Einstein and relativity, the Reverend John Michell, a British gentleman astronomer, realized this particular consequence of Newton's law of gravity and motion. In 1783, he pointed out that an object 500 times the radius of the Sun, but of the same density, would have an escape velocity greater than the speed of light. Then, all light emitted from such a body would be made to return towards it. Mitchell didn't know it, but he was talking about a black hole. If the core of a star contains more than 3 solar masses when it collapses, no force can stop it. It cannot stop collapsing when it reaches the density of a white dwarf because degenerate electrons cannot support that weight. So 3 solar masses is more than a limit of 1.4 solar masses, that is the Chandrasekhar limit. And it cannot stop when it reaches the density of a neutron star because not even degenerate neutrons can support that weight. So no force remains to stop the object from collapsing to 0 radius. As an object collapses, its density and the strength of its surface gravity increase. If an object collapses to 0 radius, its density and gravity become infinite. Mathematicians call such a point a singularity. But in physical terms, it is difficult to imagine an object of 0 radius. Some theorists believe that a singularity is impossible and that the laws of quantum physics must somehow hold the collapse at a radius of roughly 10 to the power 20 times smaller than a proton. Astronomically, it seems to make little difference. So now we're going to start about the Schwarzschild radius and Schwarzschild black holes. So if the contracting core of a star becomes small enough, the escape velocity in a region of space around it is so large that no light can escape. This means you can receive no information about an object or about a region of space near it, because it emits no light. Such a region is called a black hole. If the core of an exploding star collapsed into a black hole, the expanding outer layers of the star could produce a supernova remnant, but the core would vanish without a trace. In 1916, Albert Einstein published a mathematical theory of space and time that became known as the general theory of relativity. Einstein treated space and time as a single entity called spacetime. His equations showed that gravity could be described as a curvature of spacetime, and almost immediately, the astronomer Karl Schwarzschild found a way to solve Einstein's equations to describe the gravitational field around a single, non-rotating, electrically neutral lump of matter. That solution contained the first general relativistic description of a black hole. And non-rotating electrically neutral black holes are known as Schwarzschild black holes. In recent decades, theorists such as Roy Kerr and Stephen Hawking have found ways to apply the sophisticated mathematical equations of the general theory of relativity, electromagnetism, and quantum mechanics to describe charged rotating black holes. For this discussion, the differences are minor, and you may proceed as if all black holes are Schwarzschild black holes. Schwarzschild's solution shows that if matter is packed into a small enough volume, then space-time curves back on itself. Objects can follow paths that lead into the black hole, but no path leads out, so nothing can escape. Because not even light can escape, the inside of the black hole is totally beyond the view of the outside observer. The event horizon is the boundary between that isolated volume of space-time and the rest of the universe. And the radius of the event horizon is called the Schwarzschild radius, so we usually refer to it as the RS radius. The collapsing stellar core must shrink inside the Schwarzschild radius to become a black hole. So here we can see the singularity, here we can see the Schwarzschild radius, and here we can see the event horizon. So although Schwarzschild's work is highly mathematical, his conclusion is quite simple. The Schwarzschild radius depends only on the mass of the object. In a simple formula, g is the gravitational constant, m is the mass in kilograms, and c is the speed of light in meters per second. A bit more arithmetic shows that a 1 solar mass black hole has a Schwarzschild radius of 3 kilometers. A 10 solar mass black hole has a Schwarzschild radius of 30 kilometers, and so on. Every object has a Schwarzschild radius determined by its mass, but not every object is a black hole. For example, Earth has a Schwarzschild radius of about 1 centimeter, meaning that it could become a black hole if you squeezed it smaller than that radius. It is a common misconception to think of black holes as giant vacuum cleaners that will eventually suck in everything in the universe. A black hole is just a gravitational field, and at a large enough distance, its gravity is no greater than that of a normal object of similar mass. If the Sun were replaced by a one solar mass black hole, the orbits of the planet would not change at all. So here we can see if you fell into a gravitational field of a star, you would hit the star's surface before you fell very far. Because a black hole is so small, you could fall much deeper into its gravitational field and eventually cross the event horizon. At a distance, the two gravitational fields are the same. So this figure illustrates this by representing gravitational fields as curvature of the fabric of spacetime. Normal uncurved spacetime is represented by a flat plane, and the presence of a mass such as a star curves the plane to produce a depression. The extreme curvature around a black hole produces a deep funnel-shaped surface in this graphic representation. You can see from the graphs that the gravity of a black hole becomes extreme only when you approach close to it. Now you can check off another common misconception that may strike you as silly. Because of special effects in movies and TV, some people think black holes should actually look like funnels. Of course, the graphs of the strength of gravity around black holes look like funnels. But black holes themselves are not shaped like funnels. If you could approach a black hole, you might be able to see hot gas swirling inward, but you wouldn't be able to see the black hole itself. So what would happen if you would leap into a black hole? So before you can search for real black holes, you need to understand what theory predicts about a black hole. To explore that idea, you can imagine leaping feet first into a Schwarzschild black hole. If you were to leap into a black hole of a few solar masses from a distance of 1 AU, the gravitational pull would not be very large, and you would fall slowly at first. Of course, the longer you fell and the closer you came to the center, the faster you would travel. Your wristwatch would tell you that you fell for about 2 months by the time you reached the event horizon. Your friends who stayed behind would see something different. They would see you falling more and more slowly as you come closer to the event horizon because, as explained by general relativity, time slows down in curved space-time. This is known as time dilation. In fact, your friends would never actually see you cross the event horizon. To them, you would fall more and more slowly until you seemed hardly to move. Generations later, your descendants could focus their telescopes on you and see you still inching closer to the event horizon. You, however, would have sensed no slowdown and would conclude that you had reached the event horizon after about 2 months. Another relativistic effect would make it difficult to see you with normal telescopes. As light travels out of gravitational field, it loses energy, and its wavelength grows longer. This is known as the gravitational redshift. As you fell toward a black hole, your friends would need to observe at longer and longer wavelengths to detect you. While these relativistic effects seem merely peculiar, other effects would be quite unpleasant. If you were falling feet first, you would feel your feet, which would be closer to the black hole, being pulled in more strongly than your head. This is a tidal force, and at first it would be minor, but as you got closer to the black hole, the tidal force would become very large. Another tidal force would compress you, as both your left and your right side fell towards the center of the black hole. For any black hole with a mass like that of a star, the tidal forces would crush you sideways and stretch you lengthwise, long before you reach the event horizon. So, Mr. Tsim, you are correct. Spaghettification is the term that is being used. So, leaping feet first into a black hole, a person of normal proportion on the left would be distorted by tidal forces in the image on the right, long before reaching the event horizon around a typical black hole of stellar mass. Tidal forces would stretch the body lengthwise while compressing it laterally. Friction from this distortion would heat the body to high temperatures. So the friction from such severe distortions of your body would heat you to millions of degrees, and you would emit X-rays and gamma rays. Some people have suggested that it's possible to travel through the universe by jumping into a black hole, in one place and popping out of another somewhere far across space. That might make good for science fiction, but tidal forces would make it the unpopular form of transportation even if it worked. You now know how to find black hole, so look for a strong source of X-rays. It may be a black hole into which matter is falling and being heated. So the first X-ray telescopes reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of black holes. They tried to find one or more objects that were obviously black holes. That very difficult search is a good illustration of how the unwritten rules of science help scientists understand nature. A black hole alone is totally invisible because nothing can escape from its event horizon. But if matter flows into a black hole, it will roll through an accretion disk and become hot enough to emit X-rays before it reaches the event horizon. An isolated black hole in space will not have much matter flowing into it, but a black hole in a binary system might receive a steady flow of matter transferred from a companion star. This suggests you can search for black holes by looking closely at X-ray binaries. So do you think wormholes exist? So yes, if you look at the physics, there are compelling evidence for wormholes, but they still need to be discovered and detected. So some X-ray binaries, such as Hercules X1, contain a neutron star, and they will emit X-rays much as would a binary containing a black hole. So you can tell the difference in two ways. If the compact object emits pulses, you know it is a neutron star because the neutron star has a solid body within which powerful magnetic fields are generated. As the neutron star rotates, the magnetic field emits beams that sweep around the sky, producing pulses as they pass across Earth. A planet, its event horizon, cannot emit regular pulses like those from a neutron star. Another clue depends on the mass of the object. If the mass of the star of the compact object is greater than about 3 solar masses, it cannot be a neutron star, it must be a black hole. So question, doesn't it depend on how the universe is shaped? That I really don't know. So I'm not much of an expert on that field, but the shape of the universe could have an impact on it. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in the constellation Cygnus. It contains a supergiant star of spectral type B0 and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that X-rays were emitted by matter from the star flowing into the compact object. That object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object had to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes exist, astronomers needed a conclusive example, an object that couldn't be anything else. Cygnus X1 didn't quite pass the test when it was first discovered. Perhaps the B supergiant star was not a normal supergiant, and this portion of the system mass was incorrectly estimated. Or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis showed that a B0 star has a mass of about 25 solar masses, and a compact object is about 10 times the mass of the Sun. Astronomers concluded that matter flows from the B0 star as strong stellar wind, and much of that matter gets caught in a hot accretion disk about 5 times larger in diameter than the orbit of Earth's moon. The inner few hundred kilometers of the disk have a temperature of about 2 million Kelvin, hot enough to radiate X-rays. So, ladies and gentlemen, I see our time is up, so we will call this lecture for tonight. So we will continue on our lecture next week. So I will remain active for another minute or two. Otherwise, have a great evening. Good luck with all your tests and exams this week. And then have a wonderful evening, and I will see you all next week. I will remain active for another minute or two if you have questions. It's a pleasure. I'm glad you guys enjoyed this lecture. So our semester test will be online. So I see no further questions, so I'm also going to log off. Have a great night, everyone, and good luck with the rest of the week. See you all next week. So you see, I said the semester, yeah, we moved the semester test from the 25th because there was a clash on the 25th. I can't remember the module, but the test was scheduled at the exact same date and time. So if you think there's a clash on the 27th, please just let me know, and then I will follow up about it. But please send me a screenshot of that as soon as possible if there's a clash. So question, what all counts for marks? So that means all marks for this module. That will be your semester test. That will be that will count about 50% of your semester mark. Your moon assignment will count 40% of your semester mark. And the assignments, your quizzes will count 10% of the semester mark. So please just make sure of that and just send me, it will help. So it will help if you can send me an email with a screenshot if there is a clash, because if it's already an email form, then I can already send it to the HOD and escalate it immediately. So yes, we are only writing one semester test. It's a pleasure. So I'm also going to log off. So have a wonderful evening, and I will see you all next week.